Most memory problems do not first show up as crashes. They show up as invoices. I'm K1. Welcome to the last video of this mini-series. In the previous video, we saw how memory pressure becomes a performance problem. The two versions of the same endpoint had the same business goal, but one kept a larger object graph alive across an await. Under pressure, that one increased live memory and reduced throughput. But performance problems rarely stay as performance problems. In production, team reacts. They add memory, CPU, they scale out. And sometimes that is the right move. But sometimes it is like taking a painkiller. The pain gets quieter. The system feels better, but the cause is still there. That is what this video is about. How a performance problem quietly becomes a cloud bill. Now, I want to ask a different question. What happens if I do not fix that code and instead just give it more headroom by increasing the memory size? Because this is what often happens in real system. The service gets slow, memory looks tight, latency climbs, and the easy reaction is this: give it more room. Now, let's run the same demo again that we did in the previous video, but this time with a more headroom. In the last video, I constrained memory to about 1 GB to make the retain problem show up earlier and more clearly. This time, I am keeping the same setup, the same endpoint, and the same load, but increase the memory limit to 2 GB. So this is not still a benchmark for which endpoint is faster in isolation. What I care about here is something more specific. What changes when I give the process more room before memory pressure becomes painful? As before, I run the same workload under the same conditions and compare the baseline endpoints against the retained endpoint. The only meaningful change is the memory limit, 1 GB versus 2 GB. Now, let's compare the two runs again. This time, I'm not trying to repeat every details from the previous video. I only care about a few things. Bombardier still shows worse throughput and higher latency in the retained path. And now I look at the profiler. The retained version is still carrying a much larger memory footprint. The working set is still much higher. The same goes to the committed memory too. Generation number 1 is still noticeably larger, even if the gap is no longer as dramatic as it was under the tighter memory limit. At 1 GB, the inefficiency was loud, as we saw in the last video. At 2 GB, it became quieter. But quieter is not the same as fixed. That is the important part. Again, the exact numbers will move around a bit from run to run. What matters here is the pattern. And the pattern here is interesting. At 2 GB, the difference is less dramatic than it was at 1 GB. From the outside, the retained version looks more tolerable. The worst symptoms are softer. The service looks calmer. And that is exactly why adding headroom feels like it works. But the code did not become more efficient. The retained path is still causing the process to carry more memory than the baseline. It is still delivering less throughput for the resources it consumes. And that difference is exactly where cloud costs start to appear. And that is how a code level inefficiency turns into an infrastructure expense. Again, sometimes that is the right decision, but if the root cause is still there, then the bill is not really buying efficiency, it is buying relief. That is why I like the painkiller metaphor. So the real lesson is this: small memory decisions do not stay small. A longer object lifetime can grow the life set. A larger life set can increase runtime pressure. That pressure can reduce throughput and efficiency. And once that happens, infrastructure has to carry the cost. More memory, more CPU, more replica, higher bill. Scaling is sometimes the right answer. But Scaling before understanding often turns a code problem into a billing problem. And sometimes it makes the problem quieter without actually fixing it. And that brings us to the end of this mini series. In life, we are shaped not only by what happens to us, but by what stays with us over time. Managed memory follows a similar logic. The cost is not only in what gets created, it is in what remains, what overlaps, and what the runtime must continue carrying. That is why many memory problems in .NET do not begin with one dramatic mistake. The code looks clean, the logic is correct, each decision seems reasonable on its own. But over time, those decisions leave behind a structure that the runtime has to live with. That structure has a shape, and once that shape becomes too large, too connected, and too long-lived or too overlapping, the cost shows up elsewhere. This is the idea that I keep coming back to. Memory is not just something your code uses, it is something your code shapes. In this mini series, we started with a simple question about memory, and step by step, we followed it outward from object lifetime to GC pressure to performance and now to cost. Because memory is not just a correctness topic, it is not just a runtime topic, it is not also just a performance topic, it is also a cost topic. If you have been with me from the first video, thank you so much. Stay with me and grow with me.